Okay, so let's get back to the reaction kinetics, and then we're going to just wrap with some combustion reactions and then go for risk analysis. That's what we're just missing. So the last problems for chemistry. So we're still talking about reaction kinetics. So this problem here, like in FE format, we have this experiment that we're dealing with fluochloride. That's something we usually don't hear about. It doesn't matter what it is, but it's just telling us how this chemical degrades in the environment and what type of reaction we have. So we have a reaction of first order kinetic, and it's telling that 84% of that chemical photolyzes after 13 days of exposure to sunlight. So that means 84% is lost. So that's the thing. So we are dealing with that matter of how do I design my box? What's coming in, what's coming out? That there is not what's remaining. What's 16% is what's remaining. So that's the tricky part about that problem. Then it's saying this reaction assumes that has a first order kinetics. What's the rate constant? What's our K? See, all the K's are given in per day. So we're working with an exposure of 13 days. So K times T is already there. Just kind of apply that into the equation. But should be aware about the numbers you're dealing with. So as I explained before, we got to see what's coming in, what's coming out. So for this problem specifically, for time equals to 0, my concentration is, let's say, C0. And after 13 days, my final concentration is going to be actually, and let me draw that. So here is my experiment going on. Imagine it's a black box. It is coming in C0. Doesn't matter if it's 100, 1,000, 1. It's coming to 0. Then I know that 84% degrades. So 84%, 0.84, C0 comes as evaporation, degradation, biooxidation, name it. So how much is left for this? 16% of C0. That's what comes out. That's going to be 0.60. C0. So based on the first order kinetics, if I have my traditional equation, I can basically design this for C equals to C0 E minus KT. K is 13, K is what I want to find out, T is 13 days, C0 is C0, and C final, this guy over here, is 0.16 times C0. So it really doesn't depend on C0. So, and then you see the solution, it becomes, wow, they put all the integrals over there just to make it like a fancy solution. But if you start from the basic decaying equation, you just get you the same solution. So it gets a 0.14 per day if you just replace that in the equation. So here they're just showing in the solution what we designed before, how to get you that e power minus kt based on this equation. So that's basically like a shape just like as we designed before for a specific application. So on the time 0, concentration is C0. On the time T, the 13 days, concentration given is 0.16 C0. So basically how we design the problem. Can be done in a minute, can be a little longer if you just forgot about the equation for first order decay. But again, you don't have to do the integrals again because that's covering the chemical engineering part just with an ugly face, an ugly appearance. Same equation. So last problem for the reaction order. So we have this problem over here that's just the biological degraded contaminant following a first order reaction. It's telling us that the half-life of the contaminant is 3 weeks. and it's asking what's the reaction rate. So I'll let you work on this problem, give you 3 minutes to work on this problem because we basically haven't done this today yet. So I'm going to give you 3 minutes to work on this problem. Half-life is a concept, as the name suggests. Concentration gets to half of it was in the beginning. All right, we'll have time for the half-life problem. Alright, so let's have a look at the solution for this problem. I can see you just done that. You just finished that very fast. So this case over here, degradation, the first order. So we want to find what's the reaction coefficient, knowing that a half-life is about 3 weeks. So we're not working in terms of weeks. So we're working our reaction rates are in days. So just convert 7 days per week, 3 weeks, 21 days. So if it starts with C0, after 21 days, my concentration is a half of C0. Just putting that in the model for the decay, we have that by the final time, 21 days later, final concentration half of initial concentration. That's going to be equal to initial concentration e power minus 21k. Then you just take ln on both sides. It doesn't depend on C0, cut C0 on both sides. Take the ln, constant 0.033 per day. Very simple application, but maybe for some people in half-life, they may think that means 50% of the time. They may just put their 1.5 weeks, and they just be like a little confused about the whole idea what's up half-life, I mean. And that can be just one single way to just make your problem wrong. So that basically covers first order decaying. So basically, first order 0 sometimes also covered. So just like it's basic problems just like this, that can be like very practical and not too much time consuming. So final example for our problems that weren't covered before are problems with combustion. So combustion is a type of chemical oxidation with a higher concentration of oxygen. So we can have 2 types of combustion, complete or incomplete. Complete combustion, usually we're going to see the majority of the problems because incomplete combustion is really hard to forecast what's going to happen. For complete combustion, we have so much oxygen available that everything is going to be transformed into CO2 and water. While if you have an incomplete combustion, you have, instead of CO2 and water, you have CO, carbon monoxide, water, and then also some byproducts, something that wasn't completely burned because there wasn't enough oxygen. So that's why I said it's really hard to forecast your incomplete combustion reaction because you don't know exactly what was remaining. So most of the combustion problems we have are working with complete combustions. Complete combustions are going to be reactions basically stoichiometry proportions. And there are certain approaches to tackle a basic combustion stoichiometry problem. So let's see an example for complete combustion of certain chemicals. So first case, complete combustion of butane, C4H10. So butane over here, how do we do a complete combustion? Well, complete combustion is going to add plenty of oxygen, X of oxygen, in a way that all the butane is going to be converted into CO2 and water. You're not going to have any C410 left, C3, C2, nothing. Everything's going to be converted into CO2 and water. The problem here is finding the stoichiometric proportions. How much oxygen I need, how much carbon is going to come out, and how much water is going to come out as your reaction product. So the thing is that if we look into the products, we have oxygen in both CO2 and water. So it's really hard to tackle the oxygen as the first option, trying to solve for what's going to be X, because it's really, the oxygen is going to be divided between the two of them. So let's keep the oxygen for now. Let's look at either carbon or hydrogen, because carbon is exclusive for the CO2. There's no carbon in water. So if in the beginning I had 4 carbons, I'm going to have here a total of 4 CO2 molecules, because it's going to be 4 times 1's carbon. So Y equals to 4. That's easy to find. So we found already like what's Y. Hydrogen, on the other side, it's not in CO2, it's only in water. To find the amount of hydrogens, we have at the beginning 10. Each water has 2. I'm going to have 5 per water molecule. Then, by finding the amount of Y in Z, I know the amount of oxygens that I have. I have 4 times 2, it's 8, plus 5 times 1, that's going to make 13 oxygens. But in the other side, X is going to be 13 divided by 2. Stoichiometrically speaking, that's going to be the equation. 6.5 moles of oxygen. Some people just double everything and cut down the 13 halves, and then become just 13. Easy as that. That's basically the balance for a chemical combustion. The next guy we're going to see, it's not going to be so easy, because actually it's going to have, it's not going to be a pure hydrocarbon. It's going to have OH. So that's actually an alcohol. An alcohol with 3 carbons. Propanol. So prop is for 3 carbons, OH ox is alcohol, alcohol ends with OL, like ethanol, 2 carbons, propanol, 3 carbons. Combustion of the propanol. So for the propanol, it's going to be the same thing. It's going to add in a sufficient amount of oxygen to have CO2 and water. The thing is now the ratios are going to be different, because here we have also oxygen into our initial chemical, into the propanol. So starting calculating the amount of carbons. Have 3 carbons in the propanol, I'm going to have 3 CO2s on the other side. Y equals to 3. Hydrogens. Hydrogens, I have actually 8 on one side, 7 from the carbon chain, 1 from the alcohol function. That makes 8 hydrogens. Then here, if I have H2, 2 hydrogens per water, Z equals to 4. Then the oxygen proportions. If I have 3 times 2, 6 oxygens here, plus another 4 here, have a total of 10 oxygens. But from these 10 oxygens, 1 belongs to the alcohol. So remaining oxygens for the combustion are 9. Since this is a molecule of O2, I'm going to have 9 divided by 2. 4.5 moles of oxygen. So again, it's a weird number. So sometimes you just do everything times 2. 2 propanols, 9 oxygens, 6 carbons, dioxides, and 8 waters. Really doesn't matter. The whole idea is the stoichiometric proportion, how you do that. So let's see examples of problems of applications for combustion. So this case over here, it's going to be a problem of combustion and electrochemistry too. So it's going to be about oxidation numbers. So we're just going to have a comparison for this reaction. Given this reaction for methane complete combustion, what happened in terms of electron exchanges? So what happens to the oxidation numbers to this reaction? Yeah, that's a little tricky. We didn't talk about oxidation today and oxidation numbers, but this was something that was covered in Professor Kilduff's previous lecture. So here we're just going to bring back how to calculate the oxidation numbers for this combustion reaction. Who is oxidized, who is reduced, and we're just going to have a major overview. So the thing is, to see who was oxidized, who was reduced, what happens in terms of the reaction, we got to see before and after. What changed it into this reaction? We know that the carbon over here lost hydrogens and got oxygens, and that's totally going to affect how this carbon electrical charges are going to be measured, like the oxidation number for this carbon. Because before, carbon was sharing electrons with hydrogens. Now it's sharing of oxygens. And so it's going to be totally different in terms of oxidation numbers. So before, CH4, we know that each hydrogen has an oxidation number of 1. Plus 1. In order to make this carbon neutral, electrically speaking, the oxidation number for the carbon was -4. About the oxygen, oxygen is a pure element over here. For being a pure element, the oxidation number is 0. So now we're going to see what happened. Oxidation had the number of oxidation 0. After the reaction, it connected with carbon. So it really changed the oxidation number. Same is going to happen to the carbon. After the reaction, the CO2, we know that each oxygen has -2. So the carbon is going to be +4. From -4, the carbon went to +4. For the water, hydrogen stays as 1, oxygen stays as -2. So what happened overall? So we know that the carbon went from -4 to +4. Hydrogen stayed the same. Hydrogen, like, numbers didn't change. It was +1, here was still +1 in water. Oxygen started with 0 and ended as -2. In both sides, -2 in the carbon, -2 in water. So we had these changes. Carbon lost 8 electrons. In this case over here, each oxygen gained 2 electrons each. So we're going to have this distribution. So 4 times 2, and that gets 8 electrons total transfer. And then we have that the methane was oxidized because we have the change of the oxidation number increasing. So the methane was oxidized by O2. Which means that methane is the reducing agent, because by being oxidized, it's promoting the reduction for the other guy. And the oxygen that started as 0 and ended up as -2, it ended up being reduced. He just got electrons. And in this case, because he gained 2 electrons for each of the 4 oxygens, we have O2 as an oxidizer. O2 is promoting the reduction. It's becoming an oxidation agent, it's promoting oxidation from the methane. So they're working in these pairs, oxide reduction pairs. So basically that's how you analyze this whole structure. So let's see an example for a problem. Actually, I don't have a problem for this part specifically. For that was the problem. I mean, this was the example problem. Just put an extra slide that explained. So the second part of this chemical environmental chemistry class, we're going to talk about risk analysis and toxicology. That's also covered in environmental FE, not in the civil, just in the environmental. So for risk analysis, it's usually one problem, or maybe 2 out of 110 problems. It's a part for the FE that doesn't have as much love as it should. But the problem is there are basically application formulas. So the question is, if you never dealt with risk analysis before, you're going to do that on the day of the exam. It's going to be very time consuming because the formulas are big. It takes a whole page. So you're going to get familiar to it, and if you see something that's related, you know where to look for them. So the risk analysis formulas are actually in the manual close to the safety section. So they are close to safety, around page number 18. So there's no section exclusively in the environmental. It's not in the environmental, it's together with safety. You're going to see ergonomics, we're going to see chemical compatibility, and risk is going to be there, in the middle of lots of other topics. It's going to be associated with toxicology and occupational exposure. What do I need to know for these problems? These problems for risk are formula applications. You don't go like way too far from applying one formula or two. So luckily, it's not too complicated. The thing is, the book presents a whole chapter about toxicology. So the book is going to the manual is going to present some dose response curves. That's basically the effects of a toxicant into an organism or community. And it's going to present you some concepts such as the lethal concentration 50 and lethal dose 50, which is the dose or concentration that kills half of your population. So here in this table, as you can see, the total response that we have, lethal dose 50 kills 50% of the population. Lethal dose 10 kills 10% of the population. Has this effect, this response, exposed to a certain toxicant. We're going to see some examples of problems there, really, like just finding what's lethal dose 50. And they have this table comparing some lethal doses. So far from my experience, I have never seen a use for this table, but this table is there in the manual. So it might be something they may create a problem that's going to tell something about toxicity of PCBs or toxicity of morphine, and you're just going to think Tylenol, that's like a common headache pill. So it's just going to be all there. And then you're going to find, okay, what should I use from that? Well, that's going to compare which one has a higher lethal dose. So it's going to ask, which one, given a certain concentration, let's say 500 of morphine and 500 of Tylenol, which one has a higher dosage for killing individuals? And you can have that on the table. So basically, that's what's given there. To calculate the risk, we're going to use the carcinogenic model and the non-carcinogenic model. So this is all that you see here written down. It's not made up. It's all there, like taking 3 pages, almost 3 pages of your, almost actually 2.5 pages of your booklet. So for the carcinogenic risk, the risk is going to be given by the dose times the toxicity, which is given also translated as the intake times the slope factor. So some problems are going to be given straight away what's so-called the slope factor, that's given your threshold of response to a certain toxicant, times how much water you ingest per day. For non-carcinogenic risk, that's usually associated to metals, the expression is also going to be similar. It's going to be presenting that the hazard index that's not associated to cancer, but is also due to the hazard of exposure, is given by the same CDI, that's the chronic daily intake, divided by a reference dose. And it explains what's a reference dose. Reference dose is the one that you observed, the concentration of a non-observed adverse effect, divided by the uncertainty factor, that you convert that between mice and humans. It's just basically all given over these formulas. What is also given for these problems? You have a whole page giving you exposure values. It's going to tell you how do you calculate the CDI, the chronic dose intake. Full page explaining this. So the problems are going to have a shape that are going to tell if a woman drinks water during her lifetime, what's the risk? So here we're going to have how to calculate the dose that this woman is taking, and then you have like the top, like ingestion of drinking water is given by CW, and CW, if you look over here, is going to be your chemical concentration in water, right over here. CW, chemical in water. The intake is also considering IR. Then you look down, IR is ingestion rate, liters per day. Okay, then EF, you look down the table, exposure frequency. ED, exposure duration, divided by body weight, BW, multiplied by AT, that's the average time. It's all, the formulas are all there. So for the application, you just should look at, what are we talking about? Are we talking about water, Drinking water, contact with water, dermal contact. Are we talking about chemicals in soil? Or are we talking chemicals in vapor phase? The formulas are going to be different, but these factors are going to be given to you like what they are. For standard conditions, the next page is going to give you numbers for everything you can imagine. It's going to give you what's the average body weight for a woman, the average body weight for a man, the average body weight for a child in different age ranges, what's the amount of water an adult drinks per day, what's the amount of air a male adult breathes per day, what's the amount a female adult breathes per day. It changes from person to person. It's all different. And it's specific to certain problems. But this is all given to you, including some factors such as a year has 365 days. Wow, didn't know that. So you're going to see like all these conversion factors and all these specific exposure factors there. Never try to make that up from your head. They are going to be there in this page. So for problems, let's see an example of application. So this problem over here. Yeah, this one is going to be it's going to be a little tricky. It seems simple. It seems it's just formal application, but it's going to be a little bit more, and I'm going to explain why. So for this problem, we have this population that has 2 million people breathing air that contains 4.6 ppbs of benzene, parts per billion, which is a concentration unit that we don't work every day. Benzene is classified as a human carcinogen. The midpoint for its cancer slope factor is about 5 times 10 minus 6 per microgram per cubic meter. The carcinogenic inhalation risk is equal to the concentration in air times the cancer slope factor. Look, it's just this whole phrase is giving us the formula. The formula here is written. It's not given straight away, but you can just infer that from here that the risk is equal to the concentration in air times the slope factor. Oops, it's right here. Okay, good. So the number of additional cases of cancer in this population due to benzene is most nearly, here are the words that we hate, like it's going to be like a very close estimate for one of these answers, and see that they're not even close. 4, 40, 160, and 46,000. So really, there's no like way to get to a number that's going to be like, oh, which one is A or B? It's going to be like there's a big difference between the alternatives. So, how do we even start this problem? Well, we have like the midpoint of the cancer slope factor, and we have the concentration of benzene, but we have the concentration of benzene in ppbs. We don't have the concentration in moles per liter or milligrams per liter. We don't have, ppbs is actually not a concentration for engineering calculations. We are going to convert that into something that's going to be useful. So, first thing, ppbs, parts per billion. We have 4.6 parts of benzene in 1 billion parts of air. So we gotta do this conversion. So, first, if you're gonna see the benzene as molecular weight in terms of moles per liter, because we're talking about a concentration in moles and then in grams, we know that we are going to have here for benzene that's given the formula C6H6. We have a total of 78 grams per mole in benzene. So, okay, how that's going to help us somehow? Well, we know it's the molecular weight for the benzene. And we know that 4.6 parts per billion means that I'm going to have 4.6 moles of benzene over 10 power 9, that's 1 billion moles of air. And here we're going to have a number that was never shown before. Here we're converting moles per liter of air. We know that 1 mole of air on the normal condition of temperature and pressure, 1 mole of air has 22.4 liters. And converting liters to cubic meters, we're going to find a concentration here of moles converted in grams per liters, in this case cubic meters of air. We converted moles of air into cubic meters of air and converted moles of benzene in grams of benzene because we wanted to reach a concentration of grams per liter, grams per cubic meter, a unit of mass divided by a unit of volume. This is the problem with this problem. This is why I hate this problem, because here they never told you about this conversion factor for your air. That 1 mole of air has 22.4 liters per mole of air. So, now that we have a concentration for benzene, we finally got a consensus between the amount of moles for the amount of volume. All we're going to do is calculating the concentration, the risk, by having the concentration times the slope. That was what was written in the text. So basically, we're going to have the 16 micrograms per cubic meter multiplied by the slope factor, which was also given in micrograms per cubic meter. So that's going to give us an n-dimensional here about 8 times 10 minus 5. So risk is a probability. 8 times 10 minus 5, it's going to mean an average case in a population of 8 cases for each 10,000 cases. So 8 times 10 power minus 5 means that is 8 multiplied by 1 divided by 1,000 or 10,000. Let me just write that down over here. So this number over here, this probability, okay. Oh, let me just go back. Okay, so this probability over here, this final number that we got in a dimensional number, this means 8 times 1 divided by minus 5. So actually it's 100,000 cases. 4, 5 zeros. That's what this number for the risk means. That means we're going to have 8 cases in actually 100,000 cases. If my population has 2 million people, and I'm going to have 8 new cases for each 100,000, that's going to give a total of 160 new cases. So that's something we never worked before, so probably if you saw that maybe some discussion into introduction to environmental engineering, or even in the sometimes in water quality, water reuse, we just had some of these little aspects of risk. But this case here, risk is a probability. And this number we got here means 8 cases in 100,000. That's why I got 10 power minus 5. That's how you express this number. So for every 100,000 people, I'm going to have 8 cases. How many times 100,000 I have in 2 million? 20 times. 20 times 8 people, new people getting cancer. 20 times 8, 160 cases. That's going to be one of the alternatives back there. It's not going to even be close to, oh, actually it's exactly alternative C. Although it's the most narrowly problem, it goes exactly to alternative C. What did we learn from this problem? PPBs are really messed up. If you see a units of PPBs, be prepared for doing some kind of conversion, and the conversions are going to beat you whatever you need. I need micrograms per cubic meter. You got to convert. And PPBs start with equal things. Moles and moles, grams and grams, liters and liters. But if you start to, let's say, 4.6 liters of benzene for 10.9 liters of air, you don't know a liter of benzene. You would have maybe to do the equation PV nRT and find how much liter of benzene per mole, and then find and work from there. It would totally work for this problem. Another way to tackle this would be just finding based on PV equals to number of moles. In number of moles, you can have an idea by the mass that I have here, molecular weight. So you can just go from there. It might be a possible alternative. So another problem for risk analysis. So this one is more like toxicology. So this one here is telling us that we have tests for toxicity for thymoquinone. That's probably a type of ketone, doesn't matter, but it's tested in rats and gave us these following results. So here we have that from 10 rats that were dosed with a dose of 100 milligrams for each kilogram of body weight, 0 rats died. If I increase this dose for 500, also keeping all 10 batches, 10 mice per batch being tested, we have increased concentration, 1 dies. Increased to 1,000, 5 of them die. 1,500, 7 die. 2,000, all of the mice die. Number of rats die is 10 out of 10. According to these results, the lethal dose 50 is most nearly what? That's a real problem. It just feels like, oh, the answer is just right there. So the thing is, people who are just having this problem may not remember what LD50 means and where to find that in the manual. Toxicology. Toxicology is covered in the first 20 pages over that safety aspects for environmental chemistry. So, lethal dose 50, the dose that kills 50%. Here, I started with 10. What's the concentration that kills half of them? As simple as it seems, it's right there. 1,000 milligrams per kilogram of body weight. Just a simple analysis. If you face this problem in FE, you're just going to feel, okay, that's like a extra credit. Just go for the next one because it's really not that hard. But the problem is, LD50. If somebody has never heard what LD50 means, is going to say, I don't know, could be anything. Be any of these values, or they're going to be trying to find something back into the manual. So another example for toxicology, like in this one, I just by mistake just got answer on, but chemical reference dose. So they're talking about non-carcinogenic risks. So the chemical reference dose is the dose that you have a non-carcinogenic effects, and the toxicity increases as the chemical reference dose decreases. We saw that a reference dose back there. If we just, I know we went there too fast, but here we had the chemical reference dose. So reference dose is based on non-observed effects divided by our the total uncertainty factor in mice to humans to other species. So we have that this as decreases, the toxic effects increase. So it's basically explaining that the reference time over here is that the exposure without adverse effects. So that's another example. That's more a theoretical question for that problem specifically. So another final problem. So this case over here, we have a problem of risk that's telling that the average ingestion of methyl mercury by occupational activity is about 1 microgram per kilogram of body weight per day. And the reference dose is 0.001 milligrams per kilogram a day. The non-carcinogenic hazard index is most nearly which number? For somebody who's never heard about anything like this, they're not going to even know what to search for this. But now we know that we're going to search for and see about cancer, risk. It's going to be in the beginning of that chemical safety aspects. And the formula over there is not given in the problem. I just brought that just to remember what's the hazard index. Hazard index is given by the daily intake divided by the reference dose. And this problem is giving us that, well, the ingestion per day, the daily ingestion, 1 microgram per kilogram, the reference dose, 0.001 milligrams per kilogram a day. Actually, it's just right there, all that you need. But if you just don't know the formula, you may just waste some time searching for it. So the thing is that the index over here is dimensionless. For being dimensionless, if you're going to divide one by the other, just be aware they are in the same units. You can convert this micrograms to milligrams, or convert this milligrams to micrograms. Really doesn't matter. If you do the conversion each way you do, you're going to convert this into micrograms. It's going to be 10, and then it's going to be, or micrograms you can convert into milligrams, 0.001. It's your choice. So, as you convert, you're going to have the effect from the daily dose, that's 1 microgram converted to milligrams, divided by milligrams already given in the respective units, total of 10. So that's alternative C. Not a complicated problem, but it involves a simple formula. That's not sometimes that useful. Okay, last problem for risk analysis. This one here is going to have this tabulated values that are going to look for like men and women and ingestion and what happens. For this problem over here, we're talking about the effects of manganese in water. The median concentration in the US is about 0.07 milligrams, with 7 micrograms per liter. The lifetime ingestion by manganese by a typical adult woman that drinks well water that contains 7 micrograms. What's the total intake for the whole lifetime for this person? And then the units are milligrams per lifetime. So that gives an idea. We're talking about a woman. We got to see how much water that woman drinks every day. Then we find the amount of manganese she drinks every day, and find how much is average lifetime for this woman. No big deal. So we know that the lifetime of that table we saw before, we consider that a lifetime exposure 75 years. We know that CW is the chemical concentration in water. And EF is the exposure frequency, how much days this woman drinks water. We assume that she drinks every day the same amount of water that contains this chemical concentration, that's 0.007 milligrams per liter. The ingestion rate, how much water she drinks a day. Well, that we can find on the other table. That's going to tell that first. The amount of water ingested by an adult, 2.3 liters a day. That's all in those tables. You're going to waste a minute or two finding these numbers. The average time that we have, 360 days a year. You don't consider leap years or anything like that for this problem. Manganese concentration, 0.007. So we had that already on the condition of our problem, 0.007 milligrams per liter. To calculate the ingestion over the lifetime, well, 75 years drinking that water. Every day she drinks 0.07 milligrams per liter in a total of 2.3 liters. Multiplying the volume that is here by the concentration, we have the mass. That's the mass of manganese she drinks every day, multiplying by the amount of days, that's 365 days a year, times 75 years. Total of 440 milligrams per lifetime. The problems for risk analysis are not complicated, but they're going to require you to go back into those pages and be familiar to, and I'm going to back familiar to like this. Duration, time, average, and you can have like a variety of problems. They're going to have people swimming, people drinking water, ingestion of soil. The most severe problems you're going to have are going to have children eating soil. Yeah, there is like this coefficient of back there. So there's like the coefficient for ingestion of chemicals in soil. And then you have that children usually eat soil for certain cases. So where is the soil ingestion? That's the weirdest one. Average body soil ingestion rates way over here. So children from 1 to 6 years, they ingest more than 100 milligrams per day of soil, which is really weird to think children eating like ground, like eating like pieces of soil, but that happens. So as a person grows, like you just reduce that significantly. Like you stop like touching with your dirty hands in your mouth, you stop eating dust. But basically, it's just weird problems you can have based on this. And that can be on the creativity of the examinators, so whatever they're going to think about. We have problems with also fish. In some cases, people eating fish and shellfish. It's also going to be related to that as well. Biomagnification. And the final problem we just talked about. So, as an extra to finish this class, to wrap up this discussion, something that I didn't notice in Professor Kilba's presentation, but was about solid waste management. So probably I'm not sure if he mentioned something. I saw his materials, but I didn't see that. And since it's the course that I teach, I just decided to bring that, since it's also environmental chemistry. On the manual, we have in the very beginning of the, actually the very ending of the chemical safety, of the first 20 pages, a little bit after this risk analysis, we have what we call the waste compatibility table. You're going to have a table just like this crazy pyramid you can see over here. So this pyramid is important for hazardous waste management. And the problems you're going to have now are going to be very specific, but they just require a simple analysis of this table. It doesn't require you to be a master in chemistry. What do we have in this table? So, starting at the top, and let me see if I can zoom a little better by doing, oh, I can't go more than this. Maybe I should go to the PDF, because it's going to be better to zoom and explain this chart. So the chart is going to be, again, in the very beginning, oops, not so big, it says 57, it's around, okay, the very beginning, 15. Here, as I mentioned, right after the toxicology. Here we have toxicology section in the beginning, the doses, reference doses, carcinogenic, non-carcinogenic. Next page, hazardous waste compatibility. Oh yeah, I can get a way better zoom for this one. So this pyramid, we're going to have different chemical categories, and if you can or cannot mix them together. So starting from the top of the category, well, we start category 1, acid minerals, non-oxidizing. Then you just go there, give a number 1. All of the later categories are going to be read as, if I mix acid minerals or oxidizing materials, that's code number 2, with code number 1, that starts to read on the columns. Mixing 2 with 1, nothing happens. It's all blank. But look, some cases, if I mix, let's say, aldehydes, that's number 5. If I mix aldehydes with 2, like looking 5, 2 over here, 2 is acid or acid minerals and oxidizing materials. If I mix them together, I get these reactions represented by H and F. H, heat generation. F, fire. Shouldn't put them together for no reason. And you have these categories for like 48 different categories. The table gets really big. Oh, actually, this one is like a half a table, but there's like more than that. But there's just like, here it goes up to 21 categories and then add another like 4 at the bottom. So you have like different combinations. What's a typical problem that we have for waste compatibility, like solid waste or hazardous waste management? The problems are just like this. So, and I'm going to zoom because we're going to go back to the PDF. Let's see if I can just make it a little better. 2 typical problems. First, that one at the top named 75. So, a hazardous waste containing sodium diethyl thiocarbamate may safely be combined with, and they give categories. Just look at the table. So first, we're talking about sodium diethyl thiocarbamate. Okay, there's anything similar like that in the table? Let's see. Starting from the top. Acid minerals, organic acids, alcohols, aldehydes, compounds, hydrogens. Oh, dithiocarbamates. That's the guy. So that one is a sodium something dithiocarbamate. It's there. It's one category. So, what other guys we're talking about? Let's go back. We're talking about either aliphatic amides, ethanol, aldehydes, or organic acids. So just gotta go for the table and see like what's the compatibility. I'm gonna leave this here, and then we can go through the table and see what's the compatibility. So they react with the groups from 1 through 12. They react with 1, acid minerals. They react with 2, they react with oxidizing. They react with 3, that's the alcohol and glycols. Aldehydes, number 4. Let's see, here number 4. Hey, oh, no, 4 is alcohols and glycols, sorry. 4 is alcohols and glycols, so it doesn't interact. Number 5, aldehydes. Yeah, aldehydes generates GF and GT, that innocuous and non-flammable gas, fire, and also heat. So interactive aldehydes. So not good. Organic acids. Oh yeah, we have here organic acids is number 3. If you cross 3 with 12 down there, they do react too. So yeah, not good. So based on this, we saw that number, let's see, alcohols, number 4. Well, alcohols does not. So it's high here when you cross a dithiocarbonate with 4, that is alcohols. No reaction. Ethanol is an alcohol. That's your alternative. That's how you tackle this problem about compatibility. First, when you see that example, this question, or the FE, you don't even know what's a diethyl dithiocarbonate. And you don't have to know. You just have to know that somewhere there is a compatibility. You don't have to be a master in chemistry, but you know that you're going to have the support. So it's the same thing basically as hydraulics and the fire extinguisher that you have there. Things that we don't use every day, sprinklers, that we don't learn like every course that we go in engineering, but they are back there somewhere in the reference guide, and you should be able to go through it fast and just find that. For the next problem, it's about the same situation. We're talking about potassium, that's an alkaline earth metal, and comparing what you can combine potassium with alcohols, with organic acids, halogenated organics. Same thing, just putting that on the table and comparing with the compatibility. So basically, problems just like this. So for this case specifically, we have some time to go over. But the PDF on this left side now, and we're talking about this problem over here. Potassium, that's an alkaline earth. So let's see what there's on the table. Oh yeah, metal down here at the bottom. Metal, alkali, and alkaline earth elemental. So we're talking about this guy, 21. And we're comparing them with other components such as alcohols. Well, we learned alcohol is number 4. So alcohol is right here. So alcohol and glycol is number 4. And this is going to be like a little small because we're talking about a comparison between 4 and 21. Gee, that's going to be really small. So try to follow the line of thinking for this problem. So first, we're comparing inorganic fluorides. Oh, fluorides, inorganic. It's number 15. We're going to cross 15 with our metal, alkali, and something else. Oh yeah, that was alternative A right away. 15 crosses into this line, that's the metal alkali, and there's blank, there's no reaction. So inorganic fluorides can be mixed with potassium without no problems. How about the other one, alcohols? Alcohols over here, 4. Get down all the way to 21 row. Yeah, it does react. Heat, fire, gases. No good. Non-oxidizing mineral acids. That's at the very top of the table. So non-oxidizing minerals, number 1. Mineral acids, number 1. 1 crossing down to 21, there is reaction. Same. Heat, fire, and gases. No good. Halogenated organics. Keep down on the list. Carbamates, esters. Halogenated organics, number 17. Go down 17 with 21. Metals has H and E. This is bad. H is heat, E is explosion. So they definitely shouldn't mix. And then we found that as the first alternative, inorganic fluorides are safe. So alternative A. So basically, if you find a problem like this, giving compatibility, storage, there is where you can find this information. You don't have to know anything specific from organic chemistry or anything else, or you can have an oriented solution for this problem. That's more like an expert that has environmental chemistry and hazardous waste. Well, that basically covers these topics, and I'm happy Professor Kilduff could also have some aspects for alkalinity, hardness, and some other like environmental chemistry factors, because that actually helped me to save some time for the risk analysis. So for basic chemistry, I just recommend for this quiz, for the FE, so this quiz is just nothing. For the FE, just practice some problems. You have hundreds of problems in the database, just like these. And I must say that the problems that are in the database are harder than the ones you're going to find in the FE. So if you can do those, you're going to be prepared. But if you feel like you can't do those, or think they're too hard, you're going to see that the real ones are not going to be so hard. So you can get more certain. You can either get more confidence, or if you're totally depressed, it's either. So just try to be the overconfident. And if you're not able to solve all the problems in the database, don't feel so bad, because the real problems are going to be easier. Okay? So that concludes this meeting for today. And if you just decide to have any questions about the material, something that's online, just shoot me an email. You have my email, so just send me any questions. And I'm going to just write my email here in case for the people who are just watching this video. So that applies for them as well. So just, and the text box was just upside down. That's funny. There we go. So yeah, that's my email. If you want to send me any questions, just let me know. I can try to help with environmental chemistry, risk analysis, and also hydraulics and hydrology too. All right?